Hello everyone. Did you know that most individuals who have undergone an amputation continue to experience a vivid sensation of their missing limb? Imagine feeling your wedding ring on your finger or your watch on your wrist, despite no longer having an arm. Even more distressing that you can also feel stabbing and burning sensations. This is called the phantom limb syndrome. But why can't the brain let go of a missing limb? This video is about the presumed mechanisms of phantom limb. The sensation was first described in the 16th century by French surgeon Ambroise Paré, who noticed wounded soldiers still feeling their lost limbs. However, it wasn't until 1871 that American neurologist Silas Weir Mitchell coined the term phantom limb while treating Civil War veterans who experienced these vivid, often painful sensations. Even today, scientists have not reached a clear consensus on why phantom limb occur. Rather than one single explanation, several possible mechanisms have been proposed. Let's take a closer look at the ones that are most commonly discussed. Starting with the peripheral triggers, even though a limb is removed, the neural pathways that carry signals from that limb to the brain remain intact and functional. The wires are still there, even if the limb is gone. At the site of amputation, severed nerve endings attempt to heal and form sensitive nerve clusters called neuromas. Within these structures, the damaged nerve endings become hyperexcitable. These structures become so sensitive to physical pressure that even a light touch from a prosthesis or clothing can trigger an intense reaction. Furthermore, they can even generate their own electrical signals, known as ectopic discharges, sending them to the brain without any external stimulus at all. The brain tries to make sense of these irregular signals based on the remaining map of the lost limb, sparking the phantom sensation. Is there a map in my brain? The answer is yes. There is an area called somatosensory cortex in your brain, and it is responsible for processing sensory input from the body, such as touch, pain, and temperature. And your entire body is mapped in this area. This is a proportional distorted map because your brain maps your body based on sensitivity, not size. The more sensitive a part is, the more space it takes up in the brain. This means high sensitivity areas like your fingertips and lips occupy much larger spaces on the map due to their dense concentration of sensory receptors. This representation is called somatosensory homunculus. And this is the 3D version of homunculus. Probably not the cutest version of you. While we are born with a hardwired somatosensory homunculus, which may explain rare phantom limb sensations in those born without limbs, each person's map is uniquely reshaped by their distinct interactions with the world. For instance, the cortical representation of the left hand is significantly expanded in violinists due to intensive use. And this leads us to another proposed mechanism, which is cortical reorganization. This mechanism suggests that when an individual loses a limb, such as a hand, the corresponding hand region on the map stops receiving any sensory input. But the brain is not a static structure. It avoids leaving its neurons idle. Over time, the brain reassigns these silent neurons to serve their active neighbors on the map. For example, the face and shoulder regions, which are adjacent to the hand on the map, begin to invade this territory and take control. This leads to experiences such as when that person's face is touched, those former hand neurons fire alongside the face neurons. The brain then interprets this as a dual sensation. The person feels the touch on their face, but also experiences a phantom sensation in their missing hand. However, this mechanism suggests that this process can also lead to what is known as maladaptive plasticity. This maladaptive cortical reorganization causes the brain to struggle with conflicting sensory inputs, ultimately resulting in chronic phantom limb pain. The next mechanism, which challenges the classical reorganization theory, is cortical stability. Cortical stability suggests that the somatosensory map of a lost limb is not erased, while the former mechanism suggests that neighboring regions like the lips would invade the entire territory. New research and findings show that the core map remains intact and is not taken over completely. Instead, it persists as a resilient internal model. This visual is from a study where researchers scanned participants' somatosensory maps before amputation and for up to 5 years afterward. These brain scans show that even 5 years after losing a limb, the neural maps for the hand and lips remain remarkably stable, proving that the brain's core structure is far more resilient than the previous research suggested. Since the neural architecture remains intact, these neurons continue to fire through spontaneous activity, which creates the vivid phantom limb sensation. They suggest cortical reorganization was a popular idea for decades simply because previous studies only scanned the brain after amputation. And without a before picture, researchers mistook silence or minor signal overlaps for a total takeover of the area. This stability can also cause the concept of brain body mismatch. When the brain plans a movement, motor cortex sends a command to the muscles while simultaneously transmitting a signal of the expected outcome to the sensory center. This signal is called efferent copy. Normally, when you move your hand, the feedback from your eyes and hand matches this expectation. However, if the limb is gone, the brain issues a move command but receives no sensory feedback in return. This data conflict leads the brain to interpret the situation as a distress signal, often resulting in pain or a distorted sensation of shape and position, making the limb feel twisted or oddly sized. These were the mechanisms covered in this video. I hope this video made you more curious about the brain, because phenomena like phantom limb show us that the perception built by your brain is your reality. Thanks for watching.